Tonight we're going to travel to a world that has haunted human imagination for thousands of years. A world of rust-coloured deserts stretching to the horizon, of mountains 3 times the height of Everest, of sunsets that bleed violet across a sky the colour of a bruise. Mars, our nearest neighbour, our oldest obsession, and right now, in the minds of engineers and dreamers and the most powerful space agencies on Earth, the question is no longer whether we will send humans there. The question is which humans will go first and how many of them will come back. Here is the thing most people don't realise. The first colony on Mars, the real one, the one that gets built and inhabited and called home by actual living people, was never designed to guarantee survival. Not fully, not honestly. Buried beneath the breathtaking ambition, beneath the rocket renders and the habitat blueprints and the triumphant press conferences, is a truth that rarely gets mentioned in the headlines. The pioneers of Mars will be sent to a place that is, in almost every measurable way, trying to kill them. Radiation without mercy. Cold that makes the Antarctic feel like a summer afternoon. An atmosphere so thin it cannot sustain a single breath. And a distance from Earth so vast that if something goes wrong, no one is coming to help. By the end of tonight, you're going to understand exactly why the architects of Mars colonization knew this from the beginning and sent people anyway. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. We do not talk enough about what it means to be the first. Not the celebrated first, not the astronaut who plants a flag and returns to a ticker-tape parade. The first who stays, the first who builds, the first who looks up at a pale star in an alien sky and understands with quiet certainty that the pale star is Earth, that everything they have ever known exists inside a single point of light, 140 million miles away. There is a particular kind of courage in that moment, a particular kind of loneliness, and a particular kind of sacrifice that human civilization has always asked of its most willing souls, without ever fully admitting what it was asking. Tonight, we sit with that truth together, slowly, quietly, under the same sky those pioneers will one day leave behind. Now, let's begin. There is a moment on a clear night when you can see it, low on the horizon, brighter than most stars, with a faint reddish tint that sets it apart from everything else in the sky. It does not twinkle the way stars do. It holds steady. It glows with a kind of patient constancy, as though it has been waiting there for you specifically, as though it has always known you would eventually look up and notice it. That is Mars, and the moment you really see it, not as a point of light but as a world, something shifts inside you that is very difficult to put back the way it was. Human beings have been staring at that red light for as long as there have been human beings. The ancient Egyptians called it Her-Desher, which means the red one. The Babylonians named it Nergal, after their god of death and pestilence. The Romans gave it the name we still use today, after their god of war, because of that blood-coloured hue that made them uneasy on warm summer nights. Across thousands of years of civilization, across every culture and every continent, Mars has carried with it a particular weight, a particular darkness, as though something in the human subconscious always understood, on a level deeper than language, that this world was not welcoming, that it was something else entirely, and yet we have always dreamed of going there. That is the contradiction at the heart of everything we are going to explore tonight. We have known, in some ancient and intuitive way, that Mars is hostile. We have named it after gods of death and war. We have looked at it with a kind of reverence that is inseparable from a kind of dread. And still, the dream of standing on that surface, of breathing its air, of building something permanent beneath its alien sky, has never left us. If anything, it has grown stronger the more we have learned. And what we have learned should, by any rational measure, have made us want to stay home. The modern dream of Mars began taking real shape in the 20th century, when our telescopes grew powerful enough to resolve some of its surface features, and our imaginations did the rest. Writers and scientists alike began to sketch out what a Martian colony might look like. Pressurized domes, underground tunnels carved into ancient lava tubes, fields of crops growing under artificial light, fed by water extracted from beneath the frozen soil. It was a vision of extraordinary beauty and extraordinary ambition. It was also, in almost every detail, a vision of people living in a state of permanent, managed emergency. Every breath rationed, every calorie accounted for, every day a negotiation with an environment that had no interest in keeping them alive. Here is the thing most people do not realize when they imagine that future. The engineers and scientists who developed those plans were not naive about the dangers. They were not painting a picture of comfort and ease and a gentle new beginning for humanity. They were designing systems for survival on a planet with an average temperature of around -80 degrees Fahrenheit, a planet whose atmosphere is 95% carbon dioxide and less than 1% of the thickness of our own. A planet that receives roughly twice the radiation of Earth because it has no global magnetic field to deflect the constant stream of charged particles pouring out of the Sun and in from deep space. They knew exactly what Mars was. They built their plans around it. And in the most honest corners of those plans, they acknowledged something that never made it into the press releases, that the first people to live on Mars might not survive long enough to see it become the dream they were promised. That acknowledgement is not a footnote. It is not a minor caveat buried in a technical appendix. It is, when you sit with it quietly, the most remarkable thing about the entire enterprise. We are, as a species, considering sending living human beings to a world that is likely to kill them, on a mission that may take everything they have and give very little back, for reasons that are ultimately less about their individual survival and more about the survival of something larger. The species, the idea, the dream itself. And the people we are considering sending know this. They have always known this. Some of them are eager to go anyway. There is a particular kind of person who looks at that equation and says, yes, we will meet some of them tonight. They are not reckless people. They are not people who have failed to understand the risks or who have been deceived about what awaits them. They are people who have looked at the full picture, the distance, the radiation, the cold, the isolation, the very real possibility that they will die on that red surface far from everyone they have ever loved, and they have decided that the mission matters more than the outcome. That being part of something historic is worth more than the years they might be trading away. That a shorter life spent on the edge of the possible is worth more to them than a longer life spent watching from a safe distance. I find that both humbling and terrifying in equal measure. And I think that if you sit with it long enough tonight, you will too. Not because the thought of dying on Mars is horrifying, though it is, but because of what it reveals about us, about the species that built the pyramids and crossed the Pacific in open boats and sent 2 golden records into the darkness on the off chance that something out there might find them and understand. We have always been willing to spend lives on the dream of knowing more. We have always had people among us who volunteered to be the ones spent. The first Martian colonists are simply the latest in a line that stretches back to the very beginning of what it means to be human. Tonight, we're going to follow that line all the way to its red and dusty end. We're going to look honestly at what Mars is, at what the mission actually demands, and at the quiet, rarely spoken truth that the architects of that mission have always carried with them. Not to diminish the dream, never that. The dream is extraordinary. The dream may ultimately be the most important project our civilization has ever undertaken. But dreams built on red dust deserve to be examined honestly, with clear eyes and a steady heart. because the people who will live and possibly die inside that dream deserve no less than our full attention. They deserve to be seen, not as heroes on a poster, not as statistics in a mission report, as human beings who chose the hardest thing imaginable, with full knowledge of what they were choosing, because they believed it mattered. Tonight, we begin to understand why. Let me give you a number to hold on to tonight. 140 million miles. That is the average distance between Earth and Mars when the two planets are reasonably close to each other in their orbits around the Sun. 140 million miles. I want you to really feel that number. Not just hear it, because our minds are not built to grasp distances like this naturally. We understand miles in the context of a drive across town or a flight across a country. We do not have an instinct for the kind of emptiness that separates worlds. So let me try to give it to you in a way that lands. If you drove a car at highway speed without stopping, without sleeping, without ever slowing down, it would take you roughly 2,600 years to reach Mars at its closest approach to Earth. 2,600 years. That means if a Roman soldier had climbed into a car the day Julius Caesar was assassinated and started driving toward Mars at 60 miles per hour, that car would still be somewhere in the middle of deep space right now, with several more centuries to go before arrival. The number is so large, it becomes almost meaningless, and yet it is the number that defines everything about what a Mars colony would actually be. Not a settlement connected to home, a world unto itself, cut off in ways that have no precedent in human history. The fastest spacecraft ever launched from Earth travelled at speeds that would make that car seem laughably slow. And even so, the journey to Mars takes between 6 and 9 months, depending on the alignment of the planets. 6 to 9 months of travel through a radiation-soaked vacuum in a pressurized capsule roughly the size of a large camper van. 6 to 9 months of microgravity, which does profound and damaging things to the human body, dissolving bone density, weakening the heart, redistributing fluid in ways that affect vision and cognition. The astronauts would arrive at Mars already compromised, already diminished by the journey, and then they would have to build a life there. But the distance problem does not end when the ship lands. In many ways, it only begins. Because here is the thing most people do not realize about communicating across 140 million miles of space. Radio signals, which travel at the speed of light, take between 3 and 22 minutes to cross that gap, depending on where the two planets are in their orbits. 22 minutes. That means if a colonist on Mars sends a distress message to Earth, Earth does not receive it for up to 22 minutes. And then Earth's response takes another 22 minutes to travel back. A simple back and forth exchange, the kind of conversation you have in seconds on a phone call, takes nearly an hour on Mars. In a medical emergency, in a structural failure, in any situation where seconds matter, the colonists are completely and absolutely alone. No voice from home can reach them in time. No expert on Earth can guide them through a crisis faster than the speed of light allows. They must know everything they need to know before they leave, because there will be no calling for help when the moment comes. And the distance dictates something even more fundamental than communication. It dictates rescue, or rather, the total impossibility of it. The orbits of Earth and Mars align in a way that allows for efficient travel only once every 26 months. That window lasts a matter of weeks. If a colony on Mars falls into crisis outside of that launch window, no rescue mission can be sent. There is no going around the problem, no creative solution that physics will permit. The planets simply are not in the right position to allow it. A crew of colonists facing a catastrophic failure in the wrong month of the wrong year would have to survive on their own for potentially more than 2 years before any ship could reach them. 2 years is not an evacuation scenario. 2 years is the rest of their lives, one way or another. This is the reality that mission planners have had to sit with. and it shapes everything about how a Mars colony must be designed. Every system must be redundant, because there is no calling a repairman. Every medical procedure must be performable by the colonists themselves, because there is no hospital on Mars. Every supply of food and water and oxygen and medicine must be calculated to last far longer than expected, because the resupply ship might be delayed or lost or never sent at all. The margin for error on Mars is not slim. It is essentially non-existent. When something breaks, you fix it or you die. When someone gets sick, you treat them with what you have or you lose them. The colony must function as a perfectly self-contained civilization from the first day of landing in a way that no human settlement on Earth has ever had to function. I think about the early Antarctic expeditions sometimes when I think about Mars. The explorers of the early 20th century who travelled to the bottom of the world, to places where rescue was impossible and the environment was lethal, and the margin between survival and catastrophe was measured in days of food and degrees of temperature. Ernest Shackleton, Robert Falcon Scott, men who understood that once they crossed a certain threshold, they were beyond the reach of help. And Mars makes Antarctica look like a weekend camping trip. Antarctica is on the same planet. Antarctica shares the same atmosphere and the same gravity and the same fundamental rules. You can survive on its surface without a pressurized suit if you dress warmly enough. On Mars, you cannot step outside without technology keeping you alive. Every breath, every moment of warmth, every drop of water is something the planet will not give you. It must all be carried, manufactured, recycled, and carefully, desperately preserved. What the 140 million mile problem really means, when you reduce it to its simplest human truth, is this: the first Mars colonists will be more alone than any human beings who have ever lived. More alone than sailors on the open ocean. More alone than polar explorers in winter darkness. More alone than anyone you could name in all of recorded history. They will look up at a sky that does not contain the moon. They will watch a sun that looks smaller and colder than the one you and I know. They will go to sleep knowing that every person they have ever loved is 140 million miles away, on a pale point of light they can cover with their thumb. And they will wake up the next morning and go to work because the work is the only thing keeping them alive. That kind of aloneness changes a person. It changes a group of people, and it raises questions about human endurance that we have only begun to honestly ask. Tonight we are going to keep asking them. Close your eyes for a moment and picture Mars the way you have seen it in films and concept art, and the glossy pages of space magazines. The rust-coloured plains stretching to the horizon, the dramatic canyons cutting through ancient rock, the twin moons hanging in a salmon-pink sky. It is beautiful in its way, stark and alien and magnificent, and it is real. Those features exist, those colours are accurate, that landscape is genuinely out there waiting. But the pictures always leave something out. They leave out what it would actually feel like to stand in that landscape, what your body would experience in the first seconds after stepping outside, what Mars would do to you if your suit failed or your helmet cracked or your oxygen supply ran low. Tonight, I want to give you the real Mars, not the dream, the place itself. Let us start with the cold, because the cold is the first thing that would try to kill you. The average surface temperature on Mars is approximately -80 degrees Fahrenheit. That is not a winter in Minnesota. That is not a night at the South Pole. That is a cold so profound it exists almost entirely outside of human experience. For reference, the coldest temperature ever recorded on Earth's surface was around -129 degrees Fahrenheit, measured at a Soviet research station in Antarctica in 1983. That was an extreme outlier, a record that stands as one of the most hostile conditions our planet has ever produced. On Mars, temperatures in the polar regions during winter regularly drop to -195 degrees Fahrenheit. Not occasionally, regularly. The cold is not a weather event on Mars. It is the baseline condition of existence. And then there is the atmosphere, which is perhaps even more immediately dangerous than the cold. Mars has one technically. It is not a vacuum, but it is so thin, less than 1% of the density of Earth's atmosphere, that it offers almost none of the protections we take entirely for granted here. It cannot hold warmth the way our atmosphere does, which is why the cold is so savage. It cannot filter radiation, which is why the surface is continuously bombarded by ultraviolet light and cosmic particles. It cannot support liquid water on the surface for more than a few seconds before that water either freezes or boils away in the near vacuum conditions. And it is composed of roughly 95% carbon dioxide, 2.6% nitrogen, and less than 1% argon, with only trace amounts of oxygen. You could not breathe it for a moment. A single unprotected breath on the Martian surface would not be a breath at all. It would be the beginning of the end. The planet's size plays a role in all of this that is easy to underestimate. Mars is roughly half the diameter of Earth, and because of its smaller mass, its gravity is only about 38% of what you feel right now. That sounds almost appealing at first. You would weigh less than half of what you do on Earth. But low gravity over long periods is deeply damaging to the human body in ways that are not immediately obvious. It causes bone density loss at an accelerated rate. It weakens the cardiovascular system because the heart does not have to work as hard to pump blood against gravity. It alters the way fluid distributes through the body, creating pressure changes that affect eyesight and brain function. And critically, the low gravity of Mars also contributed to the planet losing its atmosphere in the first place. Mars was not always the desiccated, thin-aired world it is today. Billions of years ago, it had a thicker atmosphere and possibly liquid water on its surface, but its smaller size meant its interior cooled faster than Earth's, shutting down the geological activity that generates a planet's magnetic field. Without that field, the solar wind slowly stripped away the atmosphere over hundreds of millions of years. Mars lost the very thing that might have made it habitable, and it cannot get it back on any timescale that matters to us. The dust deserves its own moment, because it is one of the most insidious features of the Martian environment. The surface of Mars is covered in a fine reddish powder, made largely of iron oxide, rust essentially, along with silicates and, critically, perchlorates, which are toxic chemical compounds that occur naturally in the Martian soil. This dust gets into everything. It coats solar panels, reducing their efficiency. It works its way into mechanical joints and seals. It hangs in the atmosphere after windstorms in a suspension so fine it can take months to fully settle. And those windstorms are not gentle events. Martian dust storms can grow to cover the entire planet, blocking sunlight for weeks or months at a time and plunging solar-powered systems into an energy crisis. In 2018, a global dust storm on Mars lasted for several months and is believed to have ended the operational life of the Opportunity rover, which relied on solar power and could not survive the prolonged darkness. For a human colony, depending on solar energy to keep its air warm and its oxygen flowing, a planet-wide dust storm is not an inconvenience. It is a potential extinction event for the settlement. And beneath all of this, there is the silence. I want you to imagine the silence of Mars because it is different from any silence you have experienced on Earth. Our planet is full of sound even in its quietest places. Wind through leaves, the distant call of birds, the low hum of atmosphere moving over terrain. Mars is quieter in a way that goes beyond the absence of those things. Its thin atmosphere transmits sound so poorly that an explosion 50 feet away from you would sound muffled and distant, almost gentle. Human voices carry badly. The world is acoustically muted in a way that would feel profoundly wrong to a human brain wired for the rich sonic landscape of Earth. Early research suggests that Mars would sound eerie in a way that is difficult to simulate. Not silent exactly, but wrong, hollow, as though the planet itself was somehow absent even as you stood on it. This is the world that we are planning to send people to, not the concept art, not the rendered habitats glowing warmly against a dramatic Martian sunset. The real place, -80 degrees on an average day, toxic dust in the soil, an atmosphere that cannot support a breath, radiation pouring through the sky without mercy, dust storms that can swallow the planet, and a silence so deep it would feel like the universe itself had stopped listening. The dream of Mars is real, and it is worth dreaming. But the dream lives inside the real place, and the real place does not care about our dreams. It never has. The first colonists will land on a world that is magnificent and lethal and entirely indifferent to their presence. And from the moment they step outside, they will be negotiating with it, carefully and continuously, for every single day of their lives. There is a danger on Mars that you cannot see, cannot feel, cannot smell, and cannot hear. It produces no flash of light and no sudden pain. It does not announce itself. It simply arrives continuously from every direction, passing through habitat walls and spacesuits and human tissue with almost no resistance, and it accumulates inside your body like a slow and patient debt that will eventually come due. Radiation is, in the honest assessment of most Mars mission planners, the single greatest long-term threat to human survival on the planet. And it is the threat that receives the least attention in the public conversation about Mars colonization, perhaps because it is so invisible, so gradual, and so difficult to fully solve, that acknowledging it honestly makes the entire enterprise feel more fragile than most people are comfortable admitting. To understand why Mars has a radiation problem, you need to understand what protects you from radiation right now, tonight. As you lie here listening, Earth has two overlapping shields that together make its surface one of the most radiation-safe environments in the inner solar system. The first is its magnetic field, generated by the churning of molten iron in its outer core, which deflects the vast majority of charged particles streaming out from the sun, the solar wind, and redirects them harmlessly around the planet. The second is our atmosphere, a thick blanket of gas that absorbs and scatters the radiation that does get through, including most of the ultraviolet light and the more energetic particles that manage to slip past the magnetic shield. You benefit from both of these protections every single day of your life without ever thinking about them. On Mars, neither of them exists in any meaningful form. The magnetic field is essentially gone. The atmosphere is too thin to absorb much of anything. The surface of Mars sits fully exposed to the radiation environment of deep space. There are two main categories of radiation that would assault a Mars colonist, and they come from different sources. The first is solar particle events, intense bursts of charged particles released by solar flares and coronal mass ejections from the Sun. These events can happen with very little warning and can deliver a dangerous dose of radiation in a matter of hours. On Earth, they produce the northern and southern lights and are otherwise absorbed harmlessly. On Mars, a major solar particle event could force colonists to retreat immediately to the most heavily shielded part of their habitat and wait it out, potentially for days. The second, and in some ways more troubling category, is galactic cosmic rays. These are not from our Sun. They are high-energy particles accelerated to nearly the speed of light by supernova and other violent events elsewhere in the galaxy, and they rain down on the Martian surface continuously, from every direction, without pause. You cannot predict them. You cannot time them. You simply absorb them, day after day, in doses that accumulate steadily over time. The Curiosity rover, which has been operating on the Martian surface since 2012, carried a radiation detector that measured the dose a human being would receive both during the journey to Mars and on the surface itself. The numbers it returned were sobering. During the approximately 8-month cruise to Mars, a crew would receive radiation exposure roughly equivalent to several hundred millisieverts, a unit used to measure biological radiation dose. For context, the annual radiation limit for radiation workers in most countries is 20 millisieverts per year. A single round trip to Mars before the colonists had even set foot on the surface would expose them to many times the dose considered acceptable for an entire career of working with radiation on Earth. And then they would spend years on the surface continuing to accumulate more. The lifetime cancer risk associated with a Mars mission, by most current estimates, exceeds the limits set by space agencies for astronaut safety, which means that by the rules we currently have, a Mars mission should not be permitted, and yet it is being planned anyway. The long-term biological effects of this kind of chronic radiation exposure are not fully understood, and that uncertainty is itself part of the problem. We know that high doses of radiation damage DNA, increasing the risk of cancer over time. We know it can affect the central nervous system, potentially causing cognitive changes, memory issues, and mood disturbances in ways that would be dangerous for people who need to perform complex high-stakes tasks every single day. Some research suggests that cosmic ray exposure at the levels expected on a Mars mission may accelerate the development of conditions resembling Alzheimer's disease. We know that the gastrointestinal system is particularly sensitive to radiation, and that chronic low-level exposure disrupts gut health in ways that affect the immune system, digestion, and overall resilience. What we do not know with any certainty is exactly how a specific human body will respond to years of Martian radiation. We have never done this experiment. The first colonists would be the experiment. Engineers are not sitting passively with this problem. There are proposed solutions, and they are worth taking seriously. Underground habitats, carved into existing lava tubes or buried under several meters of Martian regolith, would provide significant shielding against both solar and cosmic radiation. Water walls, essentially surrounding living spaces with tanks of water, which is an excellent radiation absorber, have also been proposed. Certain materials, including polyethylene and hydrogen-rich compounds, absorb radiation more effectively than aluminum and could be incorporated into habitat construction. Pharmacological solutions are being researched, including compounds that might help cells repair radiation-induced DNA damage more efficiently. None of these solutions eliminates the problem. They reduce it, they manage it, they push the risk from clearly unacceptable to uncomfortably marginal. And marginal, on Mars, is the best anyone is honestly offering. What disturbs me most about the radiation problem is not the biology or the engineering, it is the honesty gap. When space agencies and private companies present Mars colonization to the public, radiation is mentioned, briefly, as a challenge that is being worked on. And that is technically true, but the full picture, that the first colonists will almost certainly receive lifetime radiation doses that would be prohibited in any occupational setting on Earth, that their long-term cancer risk is elevated in ways that current technology cannot fully mitigate, that we are genuinely uncertain about the neurological effects of years of cosmic ray exposure. That full picture rarely makes it into the conversation. The dream is too beautiful, and the radiation is too invisible, and too complicated, and too frightening to put on a recruitment poster. So it gets softened, it gets qualified, it gets buried in technical reports that most people never read. But the colonists will live inside it, every day, every night, in the walls of their habitats and in the cells of their bodies, silently accumulating the cost of being the first. There is something I find both admirable and heartbreaking about that. The people who will go to Mars will know the radiation numbers. They will have read the reports. They will have been briefed by doctors and physicists and mission planners who did not soften anything for their benefit. They will have looked at their elevated lifetime cancer risk and their uncertain neurological future, and they will have signed the forms and boarded the ship anyway. That is a kind of courage that I do not have a sufficient word for. It is not recklessness. It is not ignorance. It is the deliberate acceptance of a shortened or diminished life in exchange for something they have decided matters more. We owe it to them, at the very minimum, to look at that choice clearly, to not look away from what it costs. Imagine waking up in a room you cannot leave, not a large room, not a comfortable one, a pressurized habitat the size of a modest apartment, shared with the same small group of people, day after day, for months and then years, with no possibility of stepping outside without donning a complex suit, no possibility of driving to a different city, no possibility of calling a friend on Earth and having them answer in real time. The walls of your world are close and constant. The faces around you are the only faces you will see in person for the foreseeable future. The sounds of your environment are the sounds of machinery keeping you alive, the hum of air recyclers, the low vibration of heating systems, the occasional creak of a habitat adjusting to temperature shifts. This is not a thought experiment. This is Tuesday on Mars, and then Wednesday, and then every day for the next several years. The psychological dimension of Mars colonization is the one that receives perhaps the least rigorous public attention, and yet it may be the most decisive factor in whether a colony survives its first years. We have spent decades engineering solutions to the physical problems of living on Mars. We have far less certainty about the human mind under conditions of radical, prolonged isolation. What we do have is a growing body of research from the most Mars-like environments available to us here on Earth, and what that research tells us is both fascinating and deeply unsettling. The human mind was not built for this. It can adapt partially. It can endure sometimes. But it fractures in ways that are difficult to predict, and even more difficult to repair when it does. The most extensively studied analogue for Martian isolation is Antarctic winter-over research stations. Scientists and support staff who remain at stations like the Concordia base, operated by European and French agencies at the heart of the Antarctic plateau, experience conditions that approximate some of what Mars colonists would face. They are isolated for months at a time, unable to be evacuated due to extreme weather, confined to a small team in a small structure, in an environment that is lethal immediately outside their walls. The psychological research emerging from these stations is consistent and striking. Most winter-over personnel experience what researchers call the third quarter phenomenon, a notable deterioration in mood, motivation, and cognitive performance roughly 2/3 of the way through the isolation period. They report increased irritability, sleep disturbances, difficulty concentrating, and a pervasive sense of emotional flatness, sometimes called hibernation syndrome. These effects occur even in carefully selected, highly trained, professionally stable individuals. They occur not because something goes wrong with the mission, but simply because the human mind reaches a threshold of isolation that it cannot sustain indefinitely without cost. NASA and other space agencies have also conducted analog studies in sealed habitat environments here on Earth, including the HIC's missions in Hawaii, where crews of 6 lived in a dome on a volcanic slope for periods of up to a year, simulating the communication delays and confinement of a Mars mission. The findings from these missions reinforce the Antarctic data. Interpersonal conflict is not an occasional problem in long-duration isolation. It is a near-universal one. Crews who begin missions with strong mutual respect and excellent communication skills find, after months of close confinement, that minor irritations have calcified into significant tensions, that small personality differences that seem trivial in the early weeks have become sources of genuine friction, and that the emotional energy required to maintain positive relationships in such a compressed environment is exhausting in ways that compound over time. On Mars, there is no relief valve. You cannot take a walk in a park. You cannot spend an evening with different people. The same faces are there in the morning and in the evening and in the middle of the night when you cannot sleep. And then there is the communication delay with Earth, which does not merely complicate logistics. It does something more intimate and more damaging. It severs the emotional lifeline. The ability to call home, to hear the voice of someone who loves you, to share a moment of genuine human warmth with someone outside the walls of the habitat is one of the primary psychological anchors for isolated personnel in every analog study ever conducted. Mars colonists would not have that. They would have messages, text and audio and video files that travel for up to 22 minutes in each direction, arriving delayed and unable to respond in real time. A child's birthday missed, a parent's illness reported in a message that is already hours old by the time it arrives. A moment of crisis at home that you learned about long after there was anything you could do. The psychological literature on grief and helplessness suggests that this kind of chronic, irreducible emotional delay would be one of the most corrosive elements of the Mars experience. Not dramatic, not acute, just a slow, steady erosion of connectedness that no amount of technical preparation can fully prevent. There is also a phenomenon that psychologists studying space isolation have termed the overview effect in reverse. The overview effect is the well-documented experience of astronauts who see Earth from space and report a profound, often life-altering shift in perspective, a sudden, visceral understanding of the planet's fragility and the interconnectedness of all life on it. Mars colonists might experience something darker. Researchers have speculated about what they call Earth out-of-view phenomenon, a psychological response to the moment when Earth is no longer visible to the naked eye from the spacecraft or the planet. The place where everyone you have ever loved lives becomes invisible. It does not diminish in size gradually, the way a city does as you drive away. It simply drops below the threshold of visibility one day and is gone. The reports from analog studies and from the handful of astronauts who have travelled far enough from Earth to experience something like this suggest it can produce a profound and unexpected wave of grief, disorientation, and existential vulnerability that is not fully resolved by rational knowledge that Earth is still there. What all of this research points to is a truth that mission planners have had to confront with uncomfortable honesty. The selection of the crew for a Mars colony is at least as important as the design of its habitat, and possibly more so. The wrong group of people in a technically perfect habitat will fail. The right group of people in an imperfect habitat have a chance. The psychological criteria for Mars colonists go far beyond the standard measures of intelligence, physical fitness, and technical competence. Researchers are looking for individuals with unusually high emotional stability and resilience, exceptional capacity for conflict resolution, the ability to tolerate monotony without deteriorating, a secure attachment style that can withstand prolonged separation from loved ones, and a particular quality that is difficult to measure but consistently described in the literature as something like purposeful acceptance, the ability to find meaning in the mission itself as a substitute for the ordinary sources of human comfort that will simply not be available. Not everyone who wants to go to Mars has these qualities. Not everyone who has these qualities wants to go. Finding the overlap and then trusting it to hold under conditions no analog study has fully replicated is perhaps the most uncertain bet in the entire colonization project. And it is a bet that will be placed on human beings, on their minds, on their hearts, on the fragile, extraordinary capacity of people to hold together under pressure that no one in human history has ever faced before. Every single day of your life on Earth, you participate in a system so vast and so reliable that you almost never think about it. Trucks move through the night delivering food to warehouses. Ships cross oceans carrying grain and fruit and protein. Farmers tend fields that stretch beyond the horizon, fed by rain that falls from clouds that form over warm ocean water, all of it governed by a hydrological cycle that has been running without interruption for billions of years. You are hungry, and you open a refrigerator. You are thirsty and you turn on a tap. The infrastructure of staying alive on Earth is so deeply embedded in the fabric of the world that it has become essentially invisible. On Mars, every single element of that infrastructure must be built from nothing, maintained without outside help, and kept running perfectly in an environment that is trying to dismantle it at every opportunity. And if any part of it fails significantly, people die, not eventually, soon. Let us start with water, because water is the most immediate constraint. The human body requires a minimum of roughly 2 litres of water per day to survive, more under physical exertion, more in certain medical conditions. A small colony of, say, 6 people needs at minimum 12 litres per day just to keep everyone alive at the most basic level. Add cooking, hygiene, medical needs, and the water requirements of any plant-based food production, and the number climbs considerably. Mars does have water, which is one of the few genuinely encouraging facts about the planet. It exists as ice at the poles, as frost on the surface in certain conditions, and as subsurface ice deposits that have been identified at various latitudes. There may also be liquid water in deep subsurface reservoirs, though this remains unconfirmed. The challenge is not the existence of Martian water. The challenge is extracting it, purifying it, and doing so with machinery that must work reliably in extreme cold with no replacement parts available from anywhere closer than 140 million miles away. The extraction process being considered for Mars involves drilling into permafrost or heating ice-bearing regolith to release water vapor, which is then captured and condensed. It works in laboratory conditions. It works in engineering prototypes. Whether it works continuously, reliably, for years, in actual Martian conditions, with actual Martian dust infiltrating every seal and joint, operated by people who are tired and isolated and working with tools that were designed on Earth by engineers who could only approximate what Mars would actually be like. That is a different question. A question we will not be able to answer until people are there trying to answer it with their lives depending on the outcome. And here is the terrifying mathematical reality. A colony that loses its water extraction capability and cannot repair it within a matter of days is a colony that will not survive the month. Food is a longer equation, but no less unforgiving. Resupply missions from Earth, assuming they work perfectly and arrive on schedule, cannot realistically deliver enough food to sustain a colony indefinitely. The mass and cost of shipping calories across 140 million miles of space is staggering. A single kilogram of payload delivered to the Martian surface costs an enormous amount of energy and engineering. Shipping the tens of thousands of kilograms of food needed to feed even a small colony for years is not a sustainable strategy. The colony must eventually, and ideally quickly, grow a significant portion of its own food. And growing food on Mars presents a set of problems that make terrestrial farming look almost embarrassingly simple by comparison. The Martian soil, the regolith, is not dirt. It lacks the organic material, the microbial communities, and the nutrient balance that Earth soil has accumulated over billions of years of biological activity. It is also contaminated with perchlorates, those toxic compounds mentioned earlier, at concentrations that would kill most plants and are harmful to humans. Any crops grown in Martian regolith would need to be grown in heavily modified, treated substrate or in purpose-built hydroponic or aeroponic systems that use nutrient-rich water instead of soil entirely. These systems are promising. They can produce significant yields in compact spaces. They are already being used in analog environments and in research stations on Earth. But they are complex, they require significant energy to run, and they depend on seeds, nutrients, lighting systems, atmospheric controls, and water recycling infrastructure, all functioning in concert. The failure of any one element in that chain affects the entire food supply, and in a small colony, a reduction in food supply is not an inconvenience, it is a crisis. The caloric math is worth sitting with for a moment. An adult human performing moderate physical labour, the kind of work that building and maintaining a Mars colony would certainly require, needs somewhere between 2,500 and 3,500 calories per day to function well. Sustained caloric deficits at that level of physical demand leads to muscle wasting, immune suppression, cognitive impairment, and eventually organ failure. The colonists will be doing physically demanding work in a high-stress environment while managing the cognitive load of operating complex life support systems, and they need to be well fed to do it safely. Undernourishing the people responsible for keeping the colony alive is not a slow problem. It compounds quickly. A colony that is eating 80% of what it needs is a colony that is gradually becoming less capable of solving the problems that are causing it to eat only 80% of what it needs. It is a spiral, and it has a bottom. Then there is the question of nutritional completeness, which receives almost no attention in the popular conversation about Mars, but which matters enormously over time. A hydroponic colony might produce adequate calories through staple crops like potatoes, sweet potatoes, wheat, and legumes. But a diet built primarily on those crops, without access to the full range of vitamins, minerals, and micronutrients that a varied diet provides, will produce deficiency-related health problems over months and years. Vitamin deficiencies, mineral imbalances, the absence of certain fatty acids, these are not exotic medical concerns. They are well-documented historical problems in populations with limited food variety, and they degrade health gradually but decisively. Supplements can help, and mission planners are accounting for them. But supplements have shelf lives, and resupply ships have delays, and a colony that runs out of a critical nutrient supplement and cannot receive more for 18 months is a colony whose members are quietly becoming sicker while they work to survive. What the math of staying alive on Mars ultimately reveals is that the colony must function as a closed-loop biological system from very nearly the first day. Every molecule of water must be captured and recycled. Every gram of food must be grown or carefully rationed from carried supplies. Every calorie burned in labour must be replaced by calories produced locally as quickly as possible. The margin between a functioning colony and a failing one is not measured in months of buffer. It is measured in days of critical supply. And that thinness of margin, that precariousness built into the very arithmetic of human survival on Mars, is not a problem that will be fully solved before the first people land. It will be a problem those people live inside, manage daily, and hope, with everything they have, never tips past the point of recovery. Think about the last time something in your home broke: a pipe, an appliance, a piece of equipment you relied on every single day. Now think about how long it took to get the replacement part, the repairman, the solution. Perhaps a few hours, perhaps a day or two if you were unlucky. Even in the most remote corners of Earth, even in the most isolated human communities, a critical supply can generally be sourced and delivered within days or weeks at the outside. We live inside a supply chain so vast and so responsive that we have built our entire civilization around the quiet assumption that the things we need can be obtained. We design our homes and our hospitals and our factories with the knowledge that replacements exist, that shortages are temporary, that the network will eventually provide. On Mars, that assumption does not exist. On Mars, there is only what you brought with you, what you can make yourself, and what is currently travelling toward you on a ship that left Earth somewhere between 6 months and 2 years ago. The orbital mechanics that govern travel between Earth and Mars are not negotiable. They are written into the physics of the solar system, and no amount of engineering ambition or financial investment can rewrite them. Earth and Mars orbit the Sun at different speeds and different distances, which means the gap between them changes constantly. Every 26 months, the two planets reach a configuration called opposition, when they are relatively close and the energy required to travel between them is at its minimum. This is the launch window. Missions must depart during this window, or they must wait. A cargo ship that misses its window does not depart a few weeks late. It sits on the ground for over 2 years while the planets drift apart and then slowly realign. And a colony on Mars that is waiting for that cargo ship does not get to pause its need for whatever is on board. It simply goes without. For 26 months. That number is not a planning inconvenience. It is the skeleton around which the entire logistics of survival must be built. This creates a supply reality unlike anything in human history. Every item a Mars colony might ever need must be anticipated, listed, loaded, and launched before the colonists themselves fully understand what they're going to need. Engineers and mission planners must essentially predict the future, must foresee every mechanical failure, every medical emergency, every consumable that will run low faster than expected, and pack the answer into a cargo hold before the question has even been asked. Some of this can be addressed with sophisticated modelling and redundant systems. Some can be managed by making the colony as self-sufficient as possible from the start. But no model is perfect, and no level of self-sufficiency is complete, especially in the early years. There will be things the colony needs that no one thought to bring. There will be failures that no engineer anticipated, and those gaps will have to be endured, improvised around, or survived without. For however long it takes the next launch window to open and the next ship to arrive. The spare parts problem alone is enough to keep mission planners awake at night. A life support system capable of keeping air breathable, water available, and temperature survivable inside a Mars habitat is an extraordinarily complex assembly of components. Pumps, valves, filters, sensors, seals, fans, heating elements, control systems, and the software coordinating all of them. Thousands of individual parts, each with its own lifespan, each capable of failing in its own way. On Earth, failed components are replaced from a global supply network that stocks virtually every part ever manufactured. On Mars, the spare parts inventory is whatever fits in the cargo hold. And once those spares are used, the next supply is on a ship that has not launched yet, or that is already in transit, or that is waiting for a window that is still 14 months away. The engineering response to this problem is to design systems that fail gracefully, that can be repaired with interchangeable parts, and that can be cannibalized from less critical functions to keep more critical ones running. It is ingenious and necessary, and it is also, honestly, a strategy for managing an inevitable crisis rather than preventing one. Manufacturing on Mars, the ability to fabricate replacement components from local materials, is one of the most important long-term goals of serious colonization planning, and one of the most technically demanding. The formal term is in situ resource utilization, which means using what Mars actually provides, rather than shipping everything from home. Mars has iron oxide in abundance, it has silicon. It has minerals that could potentially be processed into useful feedstocks for fabrication. Three-dimensional printing technology has advanced to a point where metal and ceramic components can be produced with reasonable precision from raw material inputs. In theory, a sufficiently equipped colony could eventually manufacture many of its own critical parts from Martian rock and regolith. In practice, building and maintaining that manufacturing infrastructure in the early years of a colony, when labour, energy, and cognitive bandwidth are already stretched to their limits by the basic work of staying alive, places an enormous additional burden on a community that is already carrying more than any human settlement has ever been asked to carry. It is the right long-term answer. It arrives too late to help with the crises of the first years. Medical supplies present perhaps the most unforgiving version of the supply chain problem, because the consequences of running short are so immediate and so irreversible. A Mars colony will require antibiotics, surgical instruments, anesthetics, cardiac medications, psychiatric medications, wound care supplies, and hundreds of other pharmaceutical and medical items. All of them have finite shelf lives. None of them can be manufactured on Mars in any near-term scenario. The medical inventory loaded onto the first missions will be the most carefully calculated packing list in the history of human exploration. And it will still be incomplete because no one can predict exactly which colonist will fall ill, with what condition and when. A person who develops a condition requiring a medication that was not stocked faces a reality with almost no parallel in modern medicine. The treatment exists. It is available on Earth. It cannot reach the patient for potentially 2 years. That is not a supply chain problem in any ordinary sense. It is survival decided not by the quality of care available, but by the calendar of planetary orbits. What the supply chain at the edge of the solar system ultimately demands is a colony that thinks about resources in a way no human community has ever had to think about them. Not scarcity in the economic sense, where prices rise and alternatives are found elsewhere. Absolute scarcity, the kind where the thing you need either exists within your walls right now or does not exist for you at all. Every tool must be maintained long past the point where maintenance would normally yield to replacement. Every consumable must be rationed with a precision that feels almost obsessive until you understand what running out truly means in this context. Every system must be designed with its eventual failure already planned for, its replacement already staged, its final functional days already anticipated and prepared against with whatever is available. Living that way, in permanent structured readiness for the moment when something essential is no longer there, requires a discipline and a collective psychological composure that goes beyond anything ever asked of a settled human community. It asks people not just to survive on a hostile world, it asks them to survive as though survival itself is the most complex and consequential engineering project they will ever undertake. Because on Mars, from the very first day, it will be. There is a particular kind of document that exists in the history of Mars exploration that almost never gets discussed in press conferences, or highlighted in recruitment videos, or featured in the breathless news articles about the future of humanity among the stars. It is the kind of document written by engineers and mission architects and medical planners who have spent years thinking with brutal honesty about what a Mars mission actually requires, and who have arrived, in the quiet language of technical reporting, at conclusions that the public-facing version of the dream prefers not to dwell on. These documents exist. They have always existed, and what they say, when you read them carefully and resist the urge to look away, is that the first human beings sent to live on Mars may not survive long enough to see the colony become what it was promised to be. That this outcome was considered, that it was weighed, and that the mission was planned anyway. The most public and perhaps most striking example of this honest reckoning was Mars One, the Dutch non-profit that announced in 2012 a plan to send humans to Mars on a one-way mission beginning in 2024. Mars One attracted enormous media attention and more than 200,000 applicants from around the world who expressed willingness to leave Earth permanently and never return. The concept was audacious, and it captured something genuine in the human imagination. The idea that there were people willing to give everything for the chance to be the first. But in 2014, a group of researchers at the Massachusetts Institute of Technology conducted an independent technical analysis of the Mars One mission architecture and published findings that were, in the careful language of academic engineering, devastating. Their analysis concluded that the first crew would likely begin experiencing life-threatening oxygen shortages within approximately 68 days of landing. Starvation would follow within the first few years. The technology required to keep the colonists alive simply did not exist in deployable form on the timeline Mars One had proposed. The mission, as designed, was not a colony. It was, in the assessment of the MIT researchers, closer to a death sentence with a public relations strategy. Mars One eventually collapsed for financial and organizational reasons before it ever came close to launching anyone. But the significance of it lies not in its failure, but in what it revealed about the public appetite for exactly this kind of mission, and about how thin the line was between ambition and negligence in early Mars colonization planning. The people who applied to go were not uninformed. Many of them were educated, thoughtful individuals who had read the risks and concluded that the chance to be first was worth the near certainty of dying there. The organisation offering them that chance had not, in the honest assessment of independent experts, done the engineering work to keep them alive, and yet the applications kept coming. Because the dream is that powerful, because the desire to matter, to be part of something historic, to place one's name at the very frontier of human expansion, is in some people stronger than the desire to survive. NASA's own planning documents across decades of Mars study have grappled with the survival question with more rigour but similar conclusions. The agency's design reference missions, a series of technical blueprints for human Mars expeditions developed from the 1990s onward, consistently identified the same cluster of risks: radiation exposure exceeding current safety standards, medical emergencies that cannot be adequately treated with available technology, the impossibility of rapid rescue or evacuation, and long-duration life support systems whose reliability over multi-year Mars surface operations has never been demonstrated. What is striking about reading these documents is not their pessimism. They are not pessimistic exactly. They are engineering documents, and engineering documents deal in probabilities and risk mitigation. What is striking is their quiet acknowledgement that acceptable risk, in the context of a Mars mission, means something very different from what it means anywhere else. The risk levels that would ground a commercial aircraft, or halt a surgical procedure, or trigger a regulatory shutdown of a chemical plant, are in Mars mission planning sometimes classified as acceptable given the mission objectives. The mission objectives, in the end, carry more weight than the survival odds of the individuals executing them. SpaceX's internal roadmaps for Mars colonization, as described by Elon Musk in a series of presentations beginning in 2016, made this calculus explicit in a way that was remarkable for its directness. Musk stated openly that the first missions to Mars would be dangerous and that the risk of death for early colonists would be high. He compared the first Martian settlers to the early settlers of the American colonies and to the explorers who crossed unknown oceans, framing high mortality not as a failure of planning but as an inherent feature of genuine pioneering. He described the colonists as people who were prepared to die, who accepted the odds, and who chose to go anyway. This framing was controversial in some quarters and celebrated in others. What it unambiguously was, however, was honest. More honest in some respects than the polished mission presentations that surrounded it, because it named the thing that the technical documents had been carefully implying for decades, that the first people on Mars were not being sent there with a guarantee of survival. They were being sent there with a plan for survival that everyone involved knew might not be sufficient. The historical parallels that mission planners reach for when they discuss this dimension of Mars colonization are instructive. The Jamestown colony, established in Virginia in 1607, lost more than half its settlers in its first years to starvation, disease, and conflict. The expedition members who perished were not considered casualties of reckless planning. They were considered the cost of establishing a foothold. The Lewis and Clark expedition, sent by Thomas Jefferson to explore the American West in 1804, was understood from the outset to carry a significant probability of total loss. Jefferson sent them anyway, because the information they might return with was deemed worth the cost of their potential deaths. In each of these cases, the people in authority made a calculation that the goal justified the mortality risk, and the people who went made a calculation that being part of the goal was worth the mortality risk. Mars is the same calculation, made larger and colder, and more final by the distance involved. What I find most significant about the plans that admitted the danger, honestly, is not what they reveal about the missions. It is what they reveal about the people who will go. Every serious Mars colonization proposal, from the most visionary to the most technically conservative, has acknowledged in some form that the first settlers are operating in a zone of risk beyond what we normally consider acceptable for human beings in any professional context. And the people who have read those plans and said yes anyway are not people who failed to understand the risk. They are people who understood it completely and decided that the mission mattered more than their own continuation. That is not a small thing. That is, depending on how you look at it, either the most human thing imaginable or the most terrifying. Tonight, I think it might be both. In 2013, a Dutch organisation called Mars One opened its application process for the first human mission to the Red Planet. The mission was explicitly one way. There would be no return journey, no rescue option, no reunion with family or friends or the world they had always known. The people selected would leave Earth, travel to Mars, and spend the rest of their lives there, however long or short those lives turned out to be. The application fee was modest. The selection process was extensive. And in the months that followed the announcement, more than 200,000 people from over 140 countries submitted their names. 200,000 people voluntarily placed themselves in consideration for a mission that might kill them, in conditions that would certainly diminish them, on a world that has never supported a single living thing. The question of who those people were and why they said yes is one of the most quietly profound questions in the entire story of Mars colonization. The applicants were not, as some media coverage suggested, a collection of thrill seekers or people with nothing to lose. The detailed profiles that emerged from interviews and public statements painted a far more complex and in many ways more moving picture. They included school teachers and surgeons and engineers and scientists and artists. They included parents of young children who had thought carefully about what their absence would mean. They included people in their 20s who had their entire lives statistically ahead of them, and people in their 50s who felt they had lived fully enough to give what remained to something larger than themselves. They came from wealthy countries and poor ones, from cultures with strong family ties and cultures that valorized individual sacrifice, from religious traditions that found meaning in martyrdom and secular worldviews, that found meaning in scientific contribution. What they shared was not a demographic profile, it was something harder to categorize, a particular relationship with the idea of meaning, and a particular willingness to measure the value of a life by something other than its length. Psychologists who have studied populations of extreme volunteers, people who sign up for extraordinarily dangerous missions, knowing the full risk, consistently identify a cluster of characteristics that appear with unusual frequency: high tolerance for ambiguity and uncertainty, a strong internal locus of control, meaning the belief that their choices genuinely shape their outcomes rather than the reverse, unusually developed capacity for long-range thinking, the ability to sacrifice present comfort for a future they may not personally inhabit, a sense of personal narrative that is deeply connected to contribution, to the feeling that their life must leave a mark, must mean something beyond the ordinary accumulation of days, and a quality that researchers sometimes describe as transcendent motivation, which is a formal way of saying that something beyond personal survival is driving the decision, something that feels, to the person experiencing it, more important than their own continued existence. Some of the Mars One applicants spoke in terms that were explicitly about legacy. They wanted to be the names in the history books, the faces on the monument, the people future generations pointed to and said, they were the first. There is nothing cynical about that motivation. The desire to matter to the future is one of the oldest and most recognizably human impulses we possess. It is what drove explorers across unknown oceans and climbers up unscaled peaks and scientists into laboratories working on problems that would not be solved in their lifetimes. The difference on Mars is the directness of the trade. It is not simply that you might die in service of something larger. It is that you almost certainly will live a shorter and harder life than you would have otherwise, and you're choosing that deliberately with full information because the something larger feels worth it. Others spoke in terms that were more scientific. They were researchers, engineers, biologists, geologists who saw the Mars mission as the greatest scientific opportunity in human history. The chance to study a planet up close, with human ingenuity and human intuition rather than the limited sensing of a remote rover, was worth any personal cost to them. A geologist who can pick up a Martian rock and examine it in her hands, who can climb a canyon wall and read the story written in its layers with the full pattern recognition capacity of a trained human mind, can do in a single afternoon what a rover might take months to accomplish. The scientific return on human presence on Mars is so enormous that, for people whose identity is built around the pursuit of knowledge, the mission is not a sacrifice, it is a gift. The most extraordinary gift imaginable, wrapped in danger and isolation, and the permanent loss of everything familiar. And then there were the people who spoke about something quieter and harder to articulate, a feeling, long held and difficult to explain, that they did not entirely belong where they were, that the world they had been born into, for all its beauty and comfort and connection, was not quite the right size for them. People who had stood under a clear night sky since childhood and felt something pulling in a direction they could not name, who had read about space exploration with a hunger that never quite converted into satisfaction at the reading, who understood, when the Mars One announcement appeared, that this was the thing they had been waiting to be asked, even though they had not known they were waiting. This kind of applicant is perhaps the most difficult to explain rationally and the most recognizably human. The person who simply knows, in the way that the deepest convictions are always known, that this is what they are for, that their life, whatever it contains and however long it lasts, should point in this direction. What strikes me most, sitting with all of this, is that none of these people were wrong. Not in the way that matters. The thrill-seeker framing is too simple and too dismissive for what was actually being expressed in those 200,000 applications. Something genuine was speaking, something that lives in the human species at a level below the rational assessment of odds and outcomes, the same thing that drove the first humans across land bridges into unknown continents, the same thing that put Polynesian navigators into open boats with stars as their only guide, the same thing that has always placed certain people at the absolute boundary of the known and said, further, keep going, find out what is there. These people are not anomalies in the human story. They are, in a very real sense, the reason the human story has the shape it does. Every expansion of our world, every new continent reached, every mountain summited, every ocean crossed, was made possible by people who are willing to go first into conditions that were likely to kill them. The first Mars colonists are not a departure from that tradition. They are its current expression, its most extreme and most luminous form. And somewhere tonight, they are already out there, already waiting, already certain in a way that most of us will never be, that this is what their life is for. There is a question that sits at the center of the entire Mars colonization enterprise, and it is a question that the engineers and the mission architects and the billionaires with rockets tend not to linger on in public. It is not a technical question. It has no engineering solution. It cannot be resolved by a better radiation shield, or a more reliable water extractor, or a more carefully selected crew. It is a moral question, and it is this: do we have the right to send human beings to a place that will very probably shorten their lives, damage their bodies, and isolate them beyond any precedent in human history, even if they say they want to go. And behind that question, quieter and more unsettling, is a second one. Who exactly is making that decision? On behalf of what and with whose interests actually at the centre of the calculation? The philosophical tradition that most naturally supports Mars colonization is utilitarianism, the ethical framework that judges actions by their consequences and holds that the right action is the one that produces the greatest good for the greatest number of people. Under a utilitarian lens, the math of Mars colonization looks compelling. If human civilization is genuinely at risk of extinction from any number of plausible catastrophes, asteroid impact, climate collapse, pandemic, nuclear war, or any of the dozen other scenarios that serious existentiologists track with increasing urgency, then establishing a self-sustaining human presence on another planet is not merely desirable. It is arguably the most important project our species could undertake. The survival of billions of future humans, across potentially millions of years of continued civilization, could hinge on whether we manage to make humanity multiplanetary in the next century or two. Weighed against that scale of consequence, the shortened lives or elevated cancer risks of a few hundred early colonists become, in the utilitarian calculus, a tragic but acceptable cost. The many outweigh the few. The future outweighs the present. The species outweighs the individual. But utilitarianism has always had a problem with the individual, and Mars colonization makes that problem vivid and human and impossible to dismiss. The individuals being asked to pay the cost of the utilitarian calculation are real people, with real bodies and real families, and real futures that they are being asked to trade. Philosophy has a name for the error of treating people purely as instruments of larger goals rather than as ends in themselves. Immanuel Kant called it a violation of the categorical imperative, the principle that every human being must be treated as an end in themselves and never merely as a means to someone else's purpose. A Mars colonist who is sent knowing they will receive dangerous radiation doses, knowing they may die in ways that could have been prevented with better technology, knowing that their health and longevity are being exchanged for mission objectives and civilizational insurance, that colonist is, in a meaningful philosophical sense, being used. The question is whether their informed consent changes that moral calculus, and how much. Consent is the most important ethical concept in this conversation, and also the most complicated. The argument that runs through virtually every defense of high-risk Mars missions is that the colonists are adults who have been fully informed of the dangers and who have chosen freely to accept them. This argument is powerful. Bodily autonomy is a foundational value in most ethical systems, and the right of a competent adult to make informed decisions about their own risk, including decisions that others might consider unreasonable, is taken seriously across medicine, law, and philosophy. People are permitted to become soldiers knowing they may be killed. They are permitted to become test pilots and deep-sea divers and high-rise construction workers, all professions that carry mortality risks far above the general population. The Mars colonist, on this view, is simply making a more extreme version of a choice that society routinely permits and even honours. But the consent argument has edges that deserve examination. Consent, to be fully meaningful, requires not only information, but genuine freedom, the absence of coercive pressures that might compromise a person's ability to choose freely. And Mars colonization candidates, particularly in a future where the missions are real and the selection is competitive, and the cultural status of being chosen is enormous, may face subtle pressures that complicate the purity of their consent. The person who has spent 20 years training for this mission, who has structured their entire identity around being a Mars pioneer, who faces the choice between going under dangerous conditions or stepping aside and watching someone else go in their place. Is that person choosing freely? The person who comes from a background where the financial compensation of a Mars mission represents life-changing support for a family left behind on Earth. Is their consent as unconstrained as the consent of someone with abundant alternatives? These are not hypothetical concerns. They are the ordinary mechanics of how coercion operates in human systems, and they will not disappear simply because the mission is to Mars. There is also an ethical dimension to Mars colonization that almost never appears in the public conversation because it involves people who have not yet been born and therefore cannot consent to anything at all. If a Mars colony becomes self-sustaining, if people are born there, if children grow up on a planet that will damage their DNA and limit their lives, and from which they cannot practically leave, then the ethical questions expand in a direction that is genuinely difficult to navigate. The first generation chose. The second generation did not. They were born into a world their parents built, on a planet that shortens lives, in conditions that no court on Earth would consider adequate for raising children if those conditions existed in a terrestrial context. Whether the grandeur of the mission justifies imposing those conditions on people who never agreed to them is a question that humanity will need to answer before the colony is built, not after, because after is too late. What I keep returning to, sitting with all of this in the quiet of the night, is that the ethics of Mars colonization cannot be resolved by any single framework. The utilitarian argument is real, and the stakes it invokes are genuinely enormous. The Kantian concern for individual dignity is real, and the people it protects are genuinely irreplaceable. The consent argument is powerful and also imperfect in the way that consent arguments always are when the stakes are high enough and the social pressures are strong enough to shape what people feel they can choose. What this tells me is not that Mars colonization is wrong. I do not think it is wrong. I think it may be necessary in a way that transcends ordinary moral categories. What it tells me is that the people making the decisions, the agency directors and the corporate founders and the mission architects, carry a weight of ethical responsibility that is proportional to the scale of what they are asking other human beings to do. They are asking people to spend their lives, partially or entirely, on a project whose benefits will be reaped primarily by people not yet born, on a planet not yet habitable, in a future not yet guaranteed. The least they owe the people doing the spending is total honesty about the risks, about the odds, about what the mission is really for, and who it is really serving. That honesty is not optional. It is the minimum that the ethics of the situation demands, and it is the standard by which history will eventually judge every person who had the power to send someone to Mars and chose how to use it. The landing itself would be the most terrifying 18 minutes in human history. Not because anyone watching could do anything about it, but because the colonists themselves could do almost nothing about it either. The entry, descent and landing sequence for a crewed Mars mission, what engineers grimly call the 7 minutes of terror for robotic landers, extended to nearly 18 for a heavier crewed vehicle, involves a spacecraft slamming into the Martian atmosphere at roughly 12,000 miles per hour, decelerating through heat and friction and a sequence of precisely timed maneuvers, deploying parachutes in an atmosphere too thin to slow a heavy craft adequately, and then firing retro-rockets in the final seconds to arrest the descent before the vehicle meets the surface. Every step must work. Every system must fire at exactly the right moment. There is no margin for delay and no option for abort in the final phase. Either the craft lands successfully or it does not, and if it does not, the mission ends in the first moments of its surface chapter, and the people inside it end with it. But assume it works. Assume the craft settles into the rust-coloured dust with a gentleness that seems almost impossible given the violence of the journey. Assume the retro rockets cut off and the vibration dies. and there is, for just a moment, a stillness that the crew has not felt in 8 months of travel. They are on Mars. Actually, on Mars, not in transit, not in simulation, not in the careful approximation of an analog habitat somewhere in Hawaii or Utah. The real planet. The surface they have studied in photographs and data sets and mission briefings for years is now 3 inches below the floor of the vehicle. In that moment, the psychological reality of what they have done hits them in a way that no amount of preparation can fully anticipate. Some crew members in underwater habitat analogues and Antarctic station simulations report a phenomenon researchers call arrival shock, a sudden disorienting confrontation with the reality of confinement that sets in precisely at the moment the journey ends and the actual mission begins. On Mars, that shock would carry a weight of permanence that no Earth analogue can replicate. They are here. This is it. There is no going home. The first days would be consumed by survival infrastructure, not exploration. The priority sequence in virtually every serious Mars mission plan is identical. Establish life support, verify habitat integrity, confirm power systems, check communication links with Earth, assess crew health. No one steps outside in the first hours. No one plants a flag or takes a dramatic photograph on the surface. The habitat must be verified as livable before anyone leaves the lander. Sensors check atmospheric pressure, oxygen levels, carbon dioxide concentration, temperature, and structural integrity continuously, while the crew runs through checklists that have been rehearsed hundreds of times, but never under these specific conditions. On this specific day, with this specific combination of exhaustion and adrenaline, and the particular cognitive fog that follows 8 months of microgravity. If anything in those first checks comes back wrong, a seal that reads slightly low, a sensor that gives an ambiguous reading, a pressure that is not quite where it should be, the decision tree becomes complicated very quickly. Because on Mars, a slightly wrong reading is not a reason to pause and call in an expert. It is a potential emergency, and the crew is the only expert available. The first EVA, extravehicular activity, the formal term for going outside, would likely happen within the first week, once the habitat is confirmed stable and the crew has had some recovery time. The preparation for that first walk on the Martian surface would take hours. The suit donning process alone is lengthy and methodical, with multiple checks at each stage, because a suit failure outside is not a recoverable situation. The airlock depressurization takes time, and then the outer door opens and one of them steps through, and for the first time in human history, a living person stands on the surface of Mars and looks around at a world that has waited 4.5 billion years for exactly this moment. The sky's not blue. It is a muted, dusty, pinkish tan, tinted by fine particles suspended in the thin atmosphere. The sun is visible but smaller than it appears from Earth, roughly 2/3 the size, casting a light that feels slightly off, slightly cold, slightly wrong in a way that is difficult to articulate, but immediate to the senses. The horizon is close. Mars is a smaller world. The silence inside the suit is broken only by the hum of the life support pack and the sound of the wearer's own breathing. It is one of the most extraordinary moments in the history of life in this solar system, and it lasts only as long as the oxygen supply and the suit integrity allow. By the end of the first month, the rhythms of Martian life would be establishing themselves, and they would be relentless. Maintenance occupies an enormous fraction of every day. Life support systems require constant monitoring and regular servicing. Water extraction equipment must be kept running and its outputs tested. Power systems, whether solar, nuclear or both, require attention. The habitat itself subjected to daily thermal cycling as Martian temperatures swing from relatively mild midday conditions to savage overnight cold, experiences material stress that must be checked and addressed. Crops, if any have been planted, require tending. data must be collected, logged, and transmitted to Earth. And through all of this, the crew must also eat, sleep, exercise to counteract the bone and muscle loss that low Martian gravity accelerates, and maintain the psychological practices, structured social time, private space, communication with Earth however delayed, that keep them functional as human beings rather than merely as components of a life support system. Sometime in the first Martian year, which lasts approximately 687 Earth days, nearly twice as long as a year at home, something will break in a way that was not fully anticipated. This is not pessimism, it is the statistical near certainty of operating complex machinery in extreme conditions with no external support. Perhaps it is a water recycling component that fails ahead of its predicted lifespan. Perhaps it is a medical situation that the onboard supplies and training can address, but only barely, and only with improvisation that the mission planners did not script. Perhaps it is a dust storm that arrives earlier than modelled and persists longer than predicted, reducing solar power output for weeks and forcing the crew into carefully managed conservation protocols that create their own chain of secondary stresses. Whatever it is, that first major unscripted crisis will be the true test of the mission. Not the landing, not the first EVA, the moment when something important breaks in a way the plan did not account for, and 6 people in a pressurized habitat on a hostile planet 140 million miles from the nearest help have to look at each other and figure out what to do next. By the end of that first Martian year, the survivors, and the word survivors is not melodrama, it is the accurate clinical term for people who've made it through conditions designed to select against them, would be fundamentally changed. Not broken necessarily, perhaps not even diminished in the ways that matter most, but altered, carrying in their bodies and their minds the specific weight of having lived through something no human being has ever lived through before. They would know Mars in a way that no amount of remote sensing or robotic exploration can replicate. They would know it the way you know a place when it's tried to kill you, and you have stayed anyway. And they would begin the second year with the particular clarity that only comes from having survived the first. There is a discipline within aerospace engineering called failure mode analysis. It is exactly what it sounds like. Engineers sit down systematically and imagine every way a system can fail, every component that can crack or seize or short circuit or degrade, every sequence of events that could cascade from a single point of failure into a broader catastrophe. They do this not because they are pessimists or because they enjoy contemplating disaster, but because the only way to build systems robust enough to keep people alive in extreme environments is to have already thought through in exhaustive detail what happens when those systems do not work. The best failure mode analysts are people who can hold the complete picture of a catastrophe calmly in their minds, examine it from every angle, and then go home and sleep. Tonight, I want to walk through some of what that analysis looks like for a Mars colony. Not to frighten, not to suggest that these outcomes are inevitable, but because the people who will live inside these systems deserve to have someone say clearly what the engineers already know. The scenario that keeps life support engineers most acutely focused is a habitat breach. The pressurized structure that keeps the colonists alive is separated from a lethal environment by walls, seals and airlocks that are exposed to constant thermal stress, to micrometeorite impacts, to the subtle but relentless abrasion of Martian dust, and to the material fatigue that comes from years of pressure cycling. A breach does not need to be large to be dangerous. A small crack in a seal, a pinhole in a wall section, a gasket that has degraded past its safe operating threshold, any of these can produce a slow pressure loss that compounds over hours into a life-threatening situation. The colonists would have sensors monitoring pressure continuously, and a slow breach would trigger alarms in time to respond. But responding means finding the breach, which, in a complex habitat structure, can be far more difficult than it sounds, and sealing it with whatever materials and tools are available on site. If the breach is found and sealed quickly, the crisis ends. If it is not found quickly, or if the available repair materials are not adequate, the pressure continues to drop. A human being begins to lose consciousness when atmospheric pressure falls below a certain threshold. The math of how long they have before that threshold is reached is not comfortable to calculate. A more immediate and dramatic failure is a full structural compromise, a meteorite impact large enough to puncture the habitat wall significantly, or a manufacturing defect that reveals itself catastrophically under pressure load. The Martian atmosphere offers almost no protection against small meteorites that would burn up harmlessly in Earth's thicker air. The probability of a significant impact on any given habitat structure on any given day is low. But a Mars colony is not planning to operate for a day. It is planning to operate for years, and then decades. Over a long enough timeline, the improbable becomes the eventual. A catastrophic breach gives the crew seconds to reach emergency suits and sealed refugee spaces, if those exist and are close enough. The design of Mars habitats for survivability against this scenario is one of the most challenging problems in the field, and the honest answer from most engineers is that it can be made less likely but cannot be made impossible. The power failure scenario is slower and in some ways more insidious. A Mars colony depends on electrical power for virtually every system that keeps its inhabitants alive: heating, lighting, water extraction, and purification, atmospheric processing, food production, communication, medical equipment. The redundancy built into power systems, multiple solar arrays, battery storage, possibly a small nuclear reactor, is substantial precisely because power failure is not a survivable event for long. But redundancy is not immunity. A prolonged global dust storm of the kind that has been observed on Mars covering the entire planet for months reduces solar input to a fraction of nominal levels. If the colony's power budget is tight, if the battery reserves are lower than planned because of earlier power demands, if the dust on the solar panels has not been fully cleared because of EVA constraints, the margins compress in ways that force increasingly difficult choices. Which systems get power and which go into reduced mode? How long the heating can be maintained at safe temperatures versus survival temperatures? At what point the water extraction equipment has to be shut down to keep the atmospheric processes running? These are not hypothetical engineering puzzles. They are real decisions that real people would have to make in real time, with full knowledge that the wrong answer means beginning a countdown that cannot be stopped. Medical emergencies on Mars occupy a category of their own because they combine the urgency of any medical crisis with the complete absence of the infrastructure that modern medicine requires. Consider appendicitis, one of the most common surgical emergencies in otherwise healthy adults. On Earth, appendicitis is treated routinely with a surgical procedure that takes less than an hour and carries minimal risk in a properly equipped hospital. On Mars, it requires a crew member to perform emergency surgery on a colleague using whatever surgical supplies are stocked, guided by medical training that, however thorough, does not include a surgical residency in a habitat that is not a sterile operating theatre, with no blood bank and no anesthesiologist and no intensive care unit for recovery. It can be done. There are documented cases of emergency surgery performed in extremely resource-limited environments by people without formal surgical training. But the risk is vastly higher than in a hospital setting, and the recovery environment on Mars, while stressful, physically demanding, microbiologically compromised by years of closed-loop air recycling, is not one that supports healing the way a hospital ward does. A serious medical emergency on Mars is not an emergency that can be handed off to specialists. It is an emergency that the people present must solve with what they have, or not solve at all. The psychological failure scenario is perhaps the most difficult to model and the most likely to be underestimated. The Mars mission literature is careful, almost delicate, in how it discusses the possibility of severe psychiatric breakdown in a crew member during a long-duration mission. The selection process is designed to minimize this risk. The training is designed to build resilience. The mission architecture is designed to provide structure and purpose and regular contact with Earth. And despite all of that, the research on analogous environments, long-duration submarines, Antarctic winter overstations, simulated isolation studies, consistently shows that psychological decompensation can occur in carefully selected, highly trained individuals when the conditions are extreme enough and the duration is long enough. A Mars colonist who develops a severe psychotic episode, or whose depression progresses past the point where available medications and peer support can hold it, or who becomes convinced in the particular way that extreme isolation sometimes produces that the mission is wrong and the habitat walls are a prison rather than a life support system. That person is a danger to themselves and potentially to the entire colony. And the tools available to manage that situation on Mars are limited in ways that no psychiatric crisis team on Earth would consider acceptable. I want to be clear about why I am walking through these scenarios tonight, not to suggest that Mars colonization should not happen, not to paralyze the dream with the weight of its risks, but because the first colonists will carry the knowledge of every one of these failure modes with them every day as a quiet undercurrent beneath the work and the routine and the moments of genuine wonder that living on another planet would surely also contain. They will know what a breach sounds like when the pressure alarm activates. They will know what a power shortage means in terms of which systems start going offline first. They will have rehearsed the medical scenarios and the evacuation procedures and the crisis communication protocols until those responses are as automatic as breathing. And they will do all of this while also eating breakfast and tending their crops and sending messages home and watching the Martian sun set in colours that no human eye has ever seen before. The capacity to hold all of that simultaneously, the beauty and the terror, the wonder and the fragility, is what it will actually mean to be the first. Here is the central paradox of the entire Mars colonization story, the one that lives underneath all the engineering and all the ethics and all the extraordinary human portraits of the people willing to go. It is this: the first colony on Mars must be willing to fail in order for Mars colonization to eventually succeed. Not willing in a passive, resigned sense, willing in an active, structural sense. The first mission must be designed with full acknowledgement that it may not survive, that the people on it may not survive, and that this outcome, while tragic, does not constitute a failure of the larger project. The first colony is not the destination, it is the price of admission to the destination. And the people who live and possibly die inside it are not the end of the story. They are the first sentence of a story that will take centuries to complete. That is the paradox, and sitting with it honestly, without flinching and without softening it into something more comfortable, is perhaps the most important thing we can do tonight. Human history is full of this paradox, though we rarely name it so directly. The first humans to cross the land bridge from Asia into the Americas did not know they were populating a continent. They were following game, seeking food, moving because moving was the only option available to them. Many of them died in the crossing or in the first winters on the other side, or in encounters with an unfamiliar landscape that had no mercy for the unprepared. But the ones who survived had children, and those children had children, and across thousands of years, the descendants of those first terrible crossings built civilizations of extraordinary complexity and beauty across two entire continents. The pioneers who died in the crossing did not fail. They were the crossing. They were the mechanism by which the species extended itself into a new world, and their deaths were the cost that the extension required. The Polynesian navigators who crossed the Pacific in open double-hulled canoes without instruments, guided by stars and currents, and the behaviour of birds and waves, represent perhaps the most astonishing feat of exploration in human history. They reached Hawaii, Easter Island, New Zealand, islands separated by thousands of miles of open ocean, through a process that certainly involved many lost voyages, many canoes that set out and never arrived, many crews that died somewhere in the vast blue emptiness between departure and destination. We do not have the records of those losses. The successful arrivals are what history preserved, but the losses were real, and they were understood as a likely possibility by everyone who ever climbed into one of those canoes and paddled toward the horizon. The knowledge that you might not arrive was part of the price of ever finding out what was out there. The Polynesian navigators paid it, generation after generation, because the world they found on the other side was worth the price of the crossing. The early European expeditions to the polar regions made this bargain explicit in ways that the historical record preserved completely. Robert Falcon Scott reached the South Pole in January of 1912, only to find that Roald Amundsen had arrived 5 weeks before him. Scott and his 4 companions died on the return journey, killed by cold and exhaustion and a blizzard that trapped them in their tent, less than 11 miles from a supply depot that might have saved them. The loss was enormous, the grief was real, and the knowledge generated by Scott's expedition, the geological samples his team collected and carried even as they were dying, the meteorological data, the biological observations, fed directly into the scientific understanding of Antarctica that all subsequent research has built upon. Scott did not fail. He paid the price that the frontier demanded, and the frontier gave back what frontiers always give back to those who follow: a slightly clearer picture of what is possible, bought at the cost of those who went first. The Mars pioneers occupy this same structural position in the human story, but at a scale that makes all the previous examples feel almost intimate by comparison. The distance is not an ocean or a polar plateau. It is 140 million miles of radiation-soaked vacuum. The duration is not a season or a year, but potentially a lifetime. The isolation is not the most extreme ever attempted on Earth, but the most extreme ever attempted by any human being in the history of our species. And yet the logic is identical to the logic of every previous frontier. Someone must go first. The first ones will face conditions that are not yet fully understood, with tools that are not yet fully adequate, in situations that have not yet been fully anticipated. Some of them may not survive. And what they learn, in their going and their building and their enduring and possibly their dying, will be the foundation on which every subsequent Mars mission stands. They are expendable in the coldest engineering sense of that word, and they are irreplaceable in every human sense of the word. Both things are true simultaneously. That is the paradox. What makes the Martian version of this paradox different from all its historical predecessors is the degree to which it is conscious and deliberate. The people who died crossing the Bering Land Bridge did not know they were doing something historic. The Polynesian navigators who were lost at sea did not sign consent forms. Scott and his companions understood the risk they were taking, but did not set out intending to die. The Mars colonists are different. They will know, before they board the ship, exactly what the historical record of pioneering looks like. They will have read about Jamestown and Scott and the lost polar expeditions. They will have been briefed by psychologists and physicians and mission planners who have spent careers quantifying exactly how likely various bad outcomes are, and they will go, anyway, with full awareness that they are stepping into the role of the expendable pioneer, the one whose suffering and potentially whose death buys the next generation a slightly better chance. That degree of conscious self-sacrifice is something that has almost no precedent in human exploration history. It is closer to a philosophical position than an act of courage. It is a person deciding, with full information and genuine freedom to become a historical mechanism. I find myself returning to the word expendable because it is the word that the logic demands and the word that the humanity of the situation resists. These are not expendable people. They are specific, irreplaceable human beings with names and histories and people who love them and inner lives that no mission briefing has ever fully captured. And yet the mission architecture treats them of necessity as people whose loss is an acceptable outcome if the mission objectives are sufficiently advanced by their work. That tension between the human reality of the individuals and the structural role they are being asked to play is not one that can be resolved. It can only be honoured. The least we can do, those of us who will benefit from what they build and what they sacrifice, is to see them clearly. Not as symbols, not as heroes on a poster, as people who understood the paradox completely and chose to step into it anyway, because they believed that the world their sacrifice might help build was worth more than the years it might cost them. That belief is either the most rational thing a human being can hold or the most transcendent. Tonight, sitting quietly with all of this, I think it might be both. There is a way of thinking about the first Mars colony that almost never appears in the public conversation, and it requires a shift of perspective that is initially uncomfortable, but ultimately, I think, deeply clarifying. It requires setting aside, just for a moment, the question of whether the colonists survive as individuals, and asking instead a different question: what survives regardless of what happens to them? What does the colony generate, produce, transmit and leave behind that persists beyond the fate of the people who built it? Because here is the thing that the most honest mission planners have understood from the beginning. The first Mars colony was never simply about the people who go. It was always also, and perhaps primarily, about the information they send back. And information, unlike human bodies, is not vulnerable to radiation, or cold, or habitat breach, or any of the 1,000 specific ways that Mars can end a life. Information travels at the speed of light and arrives intact regardless of what happens to the sender after it is transmitted. Consider what a single year of human presence on Mars would generate in terms of scientific data, even if that year ended in catastrophe. A geologist walking across the Martian surface, picking up rocks, examining them with trained human eyes and hands, and the full pattern recognition capacity of a mind that has spent decades learning to read planetary history in stone, would produce geological insights in weeks that rover missions have taken years to approximate. The human ability to notice anomalies, to be drawn to something unexpected, to deviate from a plan because something looks interesting in a way that cannot be fully specified in advance. These are capabilities that no remote-controlled robot has ever possessed, and that no artificial intelligence currently replicates with the richness of a trained scientific mind. The geological record of Mars, its history of water and volcanism, and climate change and potential biological activity, would be read more deeply and more quickly by a human geologist on the surface than by any combination of instruments that can be remotely operated from Earth. Every sample collected and analysed, every outcrop examined, every measurement taken and transmitted to Earth represents a permanent addition to human knowledge that no subsequent catastrophe can erase. The atmospheric data collected by colonists living through actual Martian seasons would be similarly irreplaceable. Current understanding of Martian weather patterns comes from a small number of surface sensors and orbital observations. A human colony, equipped with a network of instruments, maintained and calibrated by people who can respond in real time to unexpected readings, who can reposition sensors and make judgment calls about data quality, and notice when something in the environment has changed in a way the instruments were not designed to detect. That colony would transform our understanding of Martian meteorology in ways that would directly benefit every subsequent mission. The dust storm that threatens the colony's power supply would, in being monitored and survived and documented, also become the most detailed case study of a Martian weather event ever recorded. The threats and the data are inseparable. The danger is also the observation. The biological data generated by the colonists themselves may be the most valuable of all, in a way that is rarely acknowledged and that carries with it a particular kind of poignancy. Every person who lives on Mars becomes, unavoidably, a subject in the largest and most consequential human biological experiment ever conducted. Their radiation exposure is continuously monitored. Their bone density is measured at regular intervals. Their cognitive performance is tested. Their sleep quality is tracked. Their immune function is assessed. Their psychological state is evaluated through structured interviews and behavioral observation. Every medical event they experience, every infection, every injury, every cognitive episode, every physiological adaptation to low gravity and high radiation and closed-loop atmosphere is documented and transmitted to Earth, where medical researchers and mission planners study it for what it reveals about the human body under Martian conditions. If a colonist develops a radiation-related health complication, that complication, as terrible as it is for the individual experiencing it, also provides data that directly improves the radiation shielding specifications for every habitat built after theirs. Their suffering, documented and transmitted, becomes protection for the people who come later. The engineering data may be the most immediately practical legacy of the first colony. Every system that is built and operated on Mars under real conditions generates information that no Earth-based test can fully replicate. The performance of life support systems in actual Martian thermal cycles, the degradation rate of seals and filters and pumps in real Martian dust, the effectiveness of radiation shielding designs when exposed to actual galactic cosmic rays rather than simulated doses in a laboratory, the behavior of construction materials under genuine Martian temperature, swings and atmospheric pressure differentials, every maintenance procedure performed, every repair improvised, every failure mode encountered and addressed generates engineering knowledge that feeds directly into the design of the second generation of Martian habitat, which will be safer and more reliable precisely because the first generation revealed what the models missed. The colonists who repair a failing water extractor at 2 a.m, exhausted and stressed and working by feel because the procedure they were trained on did not quite match the actual failure mode they encountered, are also, in that moment, writing the maintenance manual that will guide every technician who comes after them. Their improvisation becomes the procedure. Their hard-won knowledge becomes institutional knowledge. It survives them regardless of what happens next. There is also something that survives that is harder to quantify, but no less real. Call it proof of concept, or call it permission. Before the Wright brothers flew at Kitty Hawk in 1903, powered human flight was a dream that many serious scientists considered impossible or at minimum generations away. After December 17th of that year, the question was no longer whether it could be done, but how to do it better. The first successful flight lasted 12 seconds and covered 120 feet. It was, by any objective measure, a modest achievement, but it changed what humanity believed was possible, and that change in belief unleashed a century of aviation progress that reshaped the entire world. The first Mars colony, whatever its fate, would be that 12-second flight scaled to the dimension of planetary civilization. It would establish beyond any further argument that humans can survive on another world, that the journey can be made, that the landing can be achieved, that a human being can wake up on Mars and work and eat and think and feel and endure. That knowledge, the pure, demonstrated, undeniable knowledge that it is possible, would survive any individual failure and outlast any loss, and it would open every door that the dreamers after us need to walk through. I find great comfort in this way of thinking about the first colony, and I offer it to you tonight, not as a way of minimizing the cost of what those pioneers will pay, but as a way of understanding the full scope of what their going means. They are not only risking their lives, they are generating a legacy. Every day they spend on Mars, whether it ends in survival or in loss, adds to a body of knowledge and proof and human achievement that belongs to all of us and to every generation that comes after. The first colonists may not live to see the Mars that their sacrifice helps to build, but that Mars will carry their fingerprints in every wall and every system and every medical protocol and every piece of data that shaped it. They will be present in it permanently in the way that all pioneers are present in the worlds their courage made possible. And that presence, unlike everything else on Mars, is not vulnerable to the cold. There is a question beneath the question of Mars colonization that rarely gets asked directly, perhaps because the answer is more uncomfortable than the technical challenges, more revealing than the engineering problems, more intimate than any discussion of radiation shielding or food production or psychological resilience. The question is this: why Mars? Not in the practical sense of why Mars rather than the Moon or an orbital station or some other stepping stone into the solar system, but in the deeper sense, why does this particular red dot in the night sky exert such a gravitational pull on the human imagination? Why have we named it after gods of war and death across culture after culture for thousands of years? Why do 200,000 people volunteer for a one-way mission to a place that will likely shorten their lives? Why at this specific moment in human history, with everything that is happening on the planet we already have, are the most powerful space agencies and the wealthiest individuals alive spending hundreds of billions of dollars trying to get us to another one? I think the answer, when you follow it all the way down, says something profound and a little terrifying about what we know, somewhere beneath the optimism and the mission statements and the glossy renders of red dust horizons, about the world we are trying to leave. Mars obsesses us, I believe, because Earth frightens us, not in a way that most people articulate consciously, and not in a way that the people driving Mars colonization would necessarily frame it. But the logic is there if you look at it honestly. The argument for becoming a multi-planetary species rests on a foundation of existential risk assessment. The Earth is vulnerable. A large enough asteroid impact, a supervolcano eruption of sufficient magnitude, a pandemic of sufficient lethality, a nuclear exchange of sufficient scale, a climate shift of sufficient severity. Any of these could end human civilization as we know it, and some of them could end the human species entirely. The geological record of Earth is, among other things, a record of mass extinctions. Life on this planet has been nearly wiped out multiple times. The dinosaurs were not consulted about the asteroid. They did not have the option to diversify their planetary portfolio. We do. The drive to reach Mars is, at its most honest, a species-level response to the knowledge that putting all of our evolutionary eggs in one planetary basket is a strategy that the universe has punished before and will punish again. But there is something else in the Mars obsession that the extinction insurance argument does not fully capture, something more immediate and more personal. The 21st century is a particular kind of moment in human history. It is a moment when the scale of human impact on our own planet has become impossible to ignore, when the evidence of what industrial civilization has done to the atmosphere and the oceans and the ecosystems that support all life on Earth is visible and measurable and frightening in ways that were not true a century ago. The people who feel most urgently the need to reach Mars are, in many cases, people who are also most aware of what is happening to Earth. And I wonder sometimes whether the drive toward Mars is not only a rational response to extinction risk, but also, on some level, an emotional response to grief. A grief about what we have already lost and what we are continuing to lose on the planet that made us. A reaching toward a new beginning that is partly about the future and partly about the inability to fully face what the present has become. Mars as a mirror reflects something back at us that is worth sitting with. When we look at Mars and see a planet that lost its atmosphere, that once had liquid water on its surface and may have harboured early life, that was transformed by planetary processes over billions of years from something that might have been hospitable into the desiccated, radiation-battered world it is today. We are looking at a cautionary tale on a geological timescale. Mars did not have industrial civilization to accelerate its transformation. Its changes happened slowly, over hundreds of millions of years, driven by the cooling of its interior and the loss of its magnetic field and the slow erosion of its air by the solar wind. Earth's changes are happening faster, much faster, and the vision of a dead Mars stripped of everything that once made it potentially alive is a vision that should feel uncomfortable to us in ways that go beyond academic interest in comparative planetology. It is a picture of what a planet looks like after it loses the things that make it livable. We are not looking at an alien world when we look at Mars, we are looking at a warning, and yet the response to that warning in the minds of the people driving Mars colonization is not to slow down, but to speed up, to expand, to reach. The logic is that if Earth is at risk, the answer is not to become more dependent on Earth, but less so. To distribute the human presence across multiple worlds so that no single catastrophe can end us. There is something both admirable and deeply strange about this response. It is admirable because it is honest about the scale of the risk and serious about addressing it. It is strange because it essentially proposes solving the problem of planetary fragility by extending ourselves to another fragile planet, rather than addressing the fragility of the one we already have. The resources and ingenuity and collective human will that a Mars colony requires are staggering. The resources and ingenuity and collective human will that would be required to meaningfully stabilize the Earth's climate systems are also staggering, and arguably more directly relevant to the survival of the 8 billion people alive right now, today, on the planet that already supports them. These two projects are not necessarily in opposition, but the fact that we are more collectively excited about the one that involves rockets and red deserts than the one that involves policy and sacrifice and the hard work of changing how we live says something about us that I think deserves to be named. What Mars ultimately reflects back at us is the full complexity of what it means to be the kind of creature we are. We are the species that fouled a river and then engineered a water treatment system. We are the species that stripped a forest and then planted a new one, imperfectly, in a different place. We are the species that has always responded to the problems created by our expansion, by expanding further, by pushing the frontier outward rather than stabilizing the ground already beneath our feet. This is not a failing, exactly. It is a pattern, a deep, ancient, possibly inescapable pattern in how our kind moves through the world. Mars colonization is that pattern taken to its most extreme expression. We have damaged the planet that made us, and our response is to reach for another one, to carry ourselves and our ingenuity and our capacity for both destruction and beauty to a new world and begin again. Whether that represents the finest expression of human adaptability or a tragic repetition of our oldest mistake is a question I genuinely do not know how to answer. I suspect it is both, simultaneously, in the way that the most profound things about human nature always are. What I know is that we are going, that the pull is too strong and the fear is too real, and the dream is too old and too deeply wired into what we are. We are going to Mars because we cannot not go, and that truth, more than any engineering specification or mission architecture, is the most honest thing I can tell you about why the first colony was always going to be built, and why it was always going to cost more than anyone was fully prepared to say out loud. Sometime in the not-so-distant future, on a night that will look from the outside like any other night, a group of human beings will climb into a spacecraft and leave the Earth behind. They will lift off from a launch pad under a sky full of stars, and for a few minutes they will be able to see the planet that made them receding below, the blue and white and green of it, the impossible beauty of it, the oceans catching light, and the clouds swirling over continents in patterns that no human eye had ever seen before the space age gave us the view from above. And then the planets will begin to shrink, slowly at first and then faster as the spacecraft accelerates away, until Earth is no longer a world filling a window, but a bright point among many, indistinguishable to the naked eye from the stars that surround it. And the people in that spacecraft will turn away from the window, or perhaps they will not be able to turn away for a very long time, and they will begin the 8-month journey toward a rust-coloured dot that is, from where they started, barely visible in the night sky of the world they're leaving. I have thought about that moment many times while making this journey with you tonight, the moment of leaving. Not the launch, which will be loud and violent and adrenaline-soaked in ways that are almost incompatible with quiet contemplation, but the moment after. The moment when the noise is gone and the acceleration has settled into the steady silence of deep space transit, and the window holds nothing but stars and the shrinking light of home. What does a person feel in that moment? What does it mean to have crossed a threshold that is, in the most literal sense, one way? To have left a world that contains everyone you have ever known, every landscape you have ever loved, every smell and sound and texture that your nervous system spent a lifetime learning to call familiar, and to have done it deliberately, with open eyes, in full knowledge of what you were leaving and what you were heading toward. I think it is a feeling for which our language does not yet have a sufficient word, something beyond courage, something beyond sacrifice, something that lives in the territory where devotion and grief become the same thing. We have spent this entire night together, looking honestly at what awaits those people. The cold that makes Antarctica feel like a summer afternoon, the radiation accumulating silently in their cells day after day, the isolation so profound that the person who loves them most is a delayed message on a screen rather than a voice in the room. The food rationed and the water recycled and the air managed and the habitat monitored and the spare parts inventoried with the desperate precision of people who know there are no more where those came from. The psychological weight of confinement, the ethical weight of being expendable by design, the existential weight of knowing that if something goes catastrophically wrong, no one is coming. We have looked at all of it, we have not looked away, and now, at the end, I want to offer you something that is not a counterweight to all of that. I do not want to soften what we have explored because it deserves its full weight, but a different angle on the same truth, because those same people, in that same habitat, on that same hostile world, will also experience something that no other human beings have ever experienced, and it matters. They will watch a Martian sunrise, a real one, not a photograph, not a simulation, but the actual sun clearing the actual horizon of another world and throwing actual light across a landscape of ancient red rock that has waited 4.5 billion years for a pair of eyes to look at it. The colour of that sky at dawn is a soft blue-grey near the horizon, tinted by fine dust particles in the atmosphere, deepening through pale salmon toward the darker pinkish tan of the daytime sky. It is not an Earth sunrise. It is not trying to be. It is its own extraordinary thing, happening on a world with its own 4 billion year history of geological drama and climatic change and the quiet patience of rock and ice and dust. And a human being will watch it and feel something that the instruments will not record, and the data logs will not capture, and the mission reports will not have adequate language to describe. Something that all of the hardship and danger and sacrifice has been, among other things, the price of admission for. The sheer, overwhelming, unrepeatable privilege of being the first to see. They will look up at the night sky from the Martian surface, and they will see Earth. On a clear night when the dust is settled and the atmosphere is at its most transparent. Earth is visible from Mars as a bright blue-white star, more luminous than anything else in that alien sky, You can cover it with your thumb. Every person you have ever loved is inside that point of light. Every book ever written, every piece of music ever composed, every ocean and forest and city and child is contained within something you can blot out with your thumbnail from where you're standing. The overview effect that astronauts describe from low Earth orbit, that profound and disorienting recognition of Earth's smallness and fragility and singular beauty, must be something altogether different when experienced from 140 million miles away. Not just perspective, severance, and then, I think, something stranger still, a kind of peace. The peace of having placed yourself so far outside the ordinary world that the ordinary world becomes, paradoxically, precious and clear in a way it never was when you were inside it. We are the universe noticing itself. That is the phrase that keeps returning to me at the end of all of this. The atoms in the bodies of the Mars colonists were forged in stars that died billions of years before our sun was born. The iron in their blood was created in the final moments of a massive star's life, scattered across space in a supernova that seeded the cloud of gas and dust that eventually became our solar system and our planets and us. They carry the history of the cosmos in their cells, these people who will stand on Mars. And when they look up at the stars from a Martian night, they are the universe doing something it has never done before in all its 13.8 billion year history, looking at itself from a second world, adding a second vantage point to the long, slow process of the cosmos becoming aware of its own existence through the medium of conscious life. That is not a small thing. That is, if you let yourself feel the full weight of it, one of the most extraordinary things that has ever happened in the history of everything. And it begins with people willing to go to a place that was never designed to keep them alive. It begins with people who said yes to all of it. The cold and the radiation and the loneliness and the risk and the grief of leaving and the terrifying beauty of arriving. It begins, as all the most important things in the human story have always begun, with someone willing to go first. Thank you for staying with me through all of this tonight. It means more than I can easily say to share these long, quiet hours with curious minds who are willing to sit with the hard questions as well as the beautiful ones. If this journey moved something in you, please take a moment to like this video or subscribe to the channel. It is a simple thing, and it helps us keep making these explorations for every sleepless soul who needs something vast and real to think about in the dark. The next time you look up at the night sky and find that faint reddish point of light holding steady among the stars, think of the people who will one day look back at us from there. Think of what they gave and what they found and what they left behind. We are all, every one of us, made of the same ancient starlight. Sleep well tonight and keep looking up,